Across the vast expanse of the cosmos, stars are born within massive clouds of gas and dust called nebulae. These nebulae, often spanning light years across, are the cosmic cradles for stellar birth. Gravity plays a crucial role, pulling the gas and dust particles together. As gravity draws these particles closer, the core of the collapsing cloud begins to heat up. This dense, hot core is known as a protostar. Over millions of years, the protostar continues to gather material from its surroundings. Its temperature and pressure increase dramatically. Eventually, the core of the protostar reaches a critical temperature of about 10 million degrees Celsius. At this point, nuclear fusion ignites, marking the birth of a star. Hydrogen atoms fuse together to form helium, releasing enormous amounts of energy. This energy radiates outward, creating the brilliant light we observe from stars. The newly born star emerges from its dusty cocoon, shining brightly in the cosmic tapestry. Once a star achieves nuclear fusion, it marks the beginning of a remarkable journey through its life cycle. It enters a long, stable period known as the main sequence, where it spends the majority of its life. This is the longest stage in a star's life. During this phase, stars generate energy by fusing hydrogen into helium in their cores. This process releases an immense amount of energy, which counteracts the force of gravity trying to collapse the star. The Sun, our very own star, is currently in its main sequence stage. This stable phase allows life to flourish on Earth. It has been shining for about 4.6 billion years, and is expected to continue for another 5 billion years. This longevity is crucial for the development and sustainability of life on our planet. The vast majority of stars we observe in the night sky are also in their main sequence. These stars, like our Sun, are in a state of equilibrium, balancing the forces of fusion and gravity. The mass of a star determines its position on the main sequence and its overall lifespan. More massive stars have shorter, more intense lives. Massive stars burn hotter and brighter but have much shorter lifespans. They exhaust their nuclear fuel quickly, leading to dramatic ends. Smaller stars, on the other hand, are cooler, dimmer, and live much longer. These stars can burn their fuel slowly, allowing them to shine for billions, even trillions of years. Our Sun is considered a medium-sized star. It provides a perfect balance, offering a stable environment for life to thrive. It falls somewhere in the middle of the main sequence in terms of both temperature and lifespan. This balance is what makes our Sun so special. Smaller stars, known as red dwarfs, can live for trillions of years. These stars are the most common in the universe, and their longevity means they will outlast many other types of stars. The life expectancy of a star is intricately linked to its mass. Massive stars, many times larger than our Sun, live fast and die young. Their immense gravity creates intense pressure and heat in their cores. This leads to rapid nuclear fusion, causing them to burn through their hydrogen fuel much faster than their smaller counterparts. While a massive star might only exist for a few million years, smaller stars can persist for billions or even trillions of years. Red dwarf stars, the smallest and coolest type of star, have incredibly long lifespans. Their low mass and slow rate of fusion allow them to conserve their hydrogen fuel for incredibly long periods. Some red dwarfs are thought to be as old as the universe itself. The differences in stellar lifespans highlight the incredible diversity of stars in the cosmos. From the short-lived but brilliant blue giants to the faint but enduring red dwarfs, each star plays a unique role in the grand tapestry of the universe. As a star exhausts the hydrogen fuel in its core, it begins to evolve off the main sequence. For stars like our Sun, this marks the transition into the red giant phase. The core contracts and heats up, causing the outer layers to expand significantly. The star swells in size, becoming a red giant. The expanding outer layers engulf nearby planets, leaving behind a glowing stellar remnant. Eventually, the core becomes hot enough to fuse helium into heavier elements, such as carbon and oxygen. More massive stars evolve into supergiants, even larger and more luminous than red giants. These stellar behemoths can fuse progressively heavier elements in their cores, creating elements like neon, magnesium, and silicon. The outer layers of red giants and supergiants are eventually ejected into space, forming beautiful, planetary nebulae. These glowing clouds of gas and dust enrich the interstellar medium with heavier elements, contributing to the formation of future stars and planets. Section 5. Stellar corpses, white dwarfs, neutron stars, and black holes. The fate of a star after it exhausts its nuclear fuel depends on its initial mass. This critical factor determines whether a star will end its life quietly or in a spectacular explosion. Low to medium mass stars, like our Sun, end their lives as white dwarfs. These stars shed their outer layers, leaving behind a hot core that becomes a white dwarf. These are the dense, Earth-sized remnants of stellar cores. Despite their small size, white dwarfs are incredibly dense, with a mass comparable to that of the Sun. White dwarfs slowly cool over billions of years, eventually fading away as black dwarfs. This process takes so long that no black dwarfs are thought to exist yet in the universe. However, more massive stars meet a more dramatic end. These stars, much larger than our Sun, have a different fate awaiting them. When a massive star runs out of fuel, its core collapses under its own gravity. This collapse happens in a matter of seconds, leading to a catastrophic event. This collapse triggers a supernova explosion, one of the most powerful events in the universe. The energy released in a supernova can outshine an entire galaxy for a short period. The explosion ejects the star's outer layers into space, leaving behind an incredibly dense remnant. This remnant is what remains of the star's core. Depending on the mass of the core, this remnant can be a neutron star or a black hole. The mass of the core determines the final stage of the star's life. Neutron stars are incredibly dense objects composed almost entirely of neutrons. They are formed when the core of a massive star is compressed to the point where protons and electrons combine to form neutrons. They are only a few miles across but have a mass greater than our Sun. This incredible density means that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. Black holes, on the other hand, are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when the core of a massive star collapses to a point of infinite density, known as a singularity. Section 6. Supernovae, the universe's grand recycling program. While supernovae mark the end of a massive star's life, they also play a crucial role in the birth of new stars and planets. The immense energy released during a supernova explosion creates shockwaves that propagate through the interstellar medium. These shockwaves compress nearby clouds of gas and dust, triggering the formation of new stars. Furthermore, supernovae are responsible for creating and dispersing heavy elements throughout the universe. The intense heat and pressure within a supernova explosion allow for the fusion of elements heavier than iron, such as gold, silver, and uranium. These elements are then scattered into space, enriching the interstellar medium and providing the building blocks for future generations of stars, planets, and even life itself. Section 7. The fate of our Sun. A glimpse into the future. Our Sun, like all stars, is not immune to the passage of time. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to evolve off the main sequence. It will expand into a red giant, engulfing the orbits of Mercury, Venus, and possibly even Earth. As a red giant, the Sun will continue to fuse helium into heavier elements for a few 100 million years. Eventually, it will shed its outer layers, forming a beautiful planetary nebula. The remaining core will contract and cool, becoming a white dwarf. This white dwarf will slowly cool over billions of years, eventually fading away as a black dwarf. While the Sun's transformation into a red giant will have catastrophic consequences for any life remaining on Earth, it will also contribute to the cycle of stellar death and rebirth in the cosmos. Section 8. From death comes life. The cosmic circle continues. The death of stars, while marking the end of one chapter, simultaneously heralds the beginning of another. When a star exhausts its nuclear fuel, it undergoes a dramatic transformation, often culminating in a spectacular supernova explosion. The material ejected during supernovae and the formation of planetary nebulae enriches the interstellar medium with heavy elements. These elements, such as carbon, oxygen, and iron, are essential for the formation of new celestial bodies. These elements, forged in the hearts of stars, become the building blocks for new stars, planets, and even life itself. The cycle of stellar death and rebirth is a fundamental process that drives the evolution of galaxies. The atoms that make up our bodies, the air we breathe, and the earth beneath our feet were all once part of a star. This cosmic connection underscores the profound relationship between the universe and life on Earth. In this sense, We are all children of the stars, connected to the vast cosmic web through the cycle of stellar death and rebirth. Every atom in our body has a history that stretches back to the dawn of the universe. The study of stars and their life cycles provides us with a profound understanding of our place in the universe. By observing the heavens, astronomers can trace the life stories of stars and uncover the secrets of cosmic evolution. It reminds us that the universe is a dynamic and ever-evolving place, where death and life are inextricably intertwined. The constant birth and death of stars shape the structure and destiny of galaxies. As we continue to explore the cosmos, we gain a deeper appreciation for the beauty and wonder of the celestial tapestry, woven together by the life and death of stars. Each discovery brings us closer to understanding the grand narrative of the universe.